In the last video lecture, we learned about one challenges of using genetically modified microorganisms in fermentation process. So in this video lecture, I will talk about some more challenges that we face, and also we'll talk about how those problems can be overcome, okay, or addressed. Okay, before going to more challenges, I want to recap the challenges that we learned in the last lecture. So, the genetically modified microorganisms usually they are more susceptible to lysis. I mean, they are more susceptible to get lysed by shear forces. Why? I mean, what the purpose of using genetically modified microorganisms? So we used genetically modified organisms to produce a desired product. That means these organisms need to produce a or some foreign proteins. Okay, and as they have to do that, they need more energy. That means they use more energy for producing that foreign protein. So that's why they have less energy to produce the essential proteins which are necessary for their structural strength. For example, they may produce less protein which are important for the cell wall. Okay, so that means cell wall of the modified organisms can be weaker in comparison with their wild type. Okay, so that's why this modified or one they are more prone to get lysed if they are exposed to high shear stress. Okay. Okay, so that's why I mean when we use modified genetical organisms in fermentation process, so we have to use those fermenters which create less shear forces, such as the bubble columns and air-lift bioreactors. And they produce or generate less shear force if we compare with the steel type bioreactors. Okay. Okay, so this was one challenge. Now I'll talk about some more challenges which we have to face when we deal with a genetically modified organism. But before going to this challenge, first I want to talk about a challenge which we face for both cases. I mean, during dealing modified organisms or unmodified organisms, and it is related with oxygen. Okay, so when we have to culture I mean we have to use high density cell culture. It can be high density bacterial cell culture or high density animal or plant cell culture in fermentation. It causes a problem with the oxygen. What problem? I mean, if the cells are in high density, what that means, there are lots of cells. So lots of cells, they will require lots of oxygen. Okay, so that means the oxygen in the media in the fermenter will rapidly deplete, which will cause a anaerobic condition, and it will be I mean it will harm the growth of the microorganisms, especially for the aerobic organisms. Okay, so if you want to use culture aerobic bacteria in the fermenter, the aerobic bacteria they need more organisms, and if you have to culture them in high dense condition, the oxygen depletion will be more faster. Okay, and especially if the size of the fermenter is big, this problem is more acute. Okay, so how this problem can be addressed or solved? So to solve these problems, chemical engineers they have attempted several approaches. Okay, by using those approaches, the amount of oxygen can be increased in the fermenter media. Okay, so what are those approaches? One, instead of asperging air, we can asperge directly oxygen. Okay, we will not. Usually in fermentation, people asperge air to supply oxygen. But in these cases, where oxygen requirements is high, in that case, instead of air, pure oxygen can be aspersed into the media. Okay, and and introducing the air or oxygen under pressure, in high velocity. To approach, another approach can be like, uh, we can use chemical which will increase the solubility of oxygen. Okay, usually the solubility of oxygen into the fermenter, into the liquid, especially into the water, is low. Okay, so that's why, when we have to cultivate a high density cell culture, even if we asperge, lots of air, it cannot solve the problem, because okay, we are asperging lots of air. The that means more oxygen will get soluble in the water, but yet still it will be low, because the original solubility of oxygen to water is itself low. Okay, so we can increase it by using chemicals. There are some chemicals such as perfluorocarbons. Okay, this chemical increase the solubility of oxygen. Okay, and another approach, modifying the configuration of the fermentation vessel to optimize the aeration or agitation of the fermentation broth. Okay, we actually can do that. So, this is related with the mass transfer. Okay, so oxygen will, oxygen, when oxygen will, dissolve in the water. Okay, so this process is called mass transfer. Oxygens are in the bubble, so they need to get into the water. This is called mass transfer. So if we can configure, by changing the configuration of the fermentation, we can optimize this process. Okay, so in that case, basically the aeration and agitation, this process is important for this optimization. Okay, okay. So by doing this, the problem with the oxygen, regarding the related with the oxygen, can be solved. Another thing can be done. Okay, what's that approach? Like, uh, say, the cells, they require oxygen for growth. So if we can modify the organisms, we can do all these approaches to solve this problem. But if we can do something more in addition, that will be great, right? So an alternative of this, okay, or you can say an addition of this, was done by two scientists named Bailey and co-workers. Okay, they designed a biological system in which the host organism was modified so that it would be more efficient at using the low levels of oxygen that are normally present in the growth media. So how we can modify the organism? Thus, the organisms will be able to absorb and utilize more oxygen, or utilize oxygen more efficiently. Okay, by inserting some gene into them. Okay, actually there are gene, a gene was collected from a gram-negative bacterium named Vitriosilla. Okay, and this gene, it's encoded protein, hemoglobin-like protein. Okay, and this protein can absorb the oxygen more efficiently. So scientists actually did that. Okay, they isolated this gene from this bacteria and introduced it into several different recombinant bacteria. Okay, and it was shown, it was observed that these recombinant bacteria are more efficient in utilizing the oxygen, even if the concentration of oxygen is low in the media. Okay, so these are some approaches by which the problem regarding the oxygen, a low availability of oxygen, can be resolved. Okay. Okay. So now let's talk about some more problem, challenge or challenges. Another challenge, we have to face when you deal with recombinant microorganism, is that they lose. They tend to lose the plasmid. Okay, what kind of problem is this? Okay, in case of, in case of, many genetically modified organisms, we introduce plasmid into them. Like, for example, say you want to produce antibiotic. You choose, say, think like this, right? So E. coli, okay, you want a E. coli bacteria to produce antibiotic for you. So what you can do? You can insert the antibiotic producing gene into your plasmid, then can insert this plasmid into your E. coli cell. So in that case, your bacteria, I mean your E. coli, will produce the antibiotic. Okay, but there is a problem when you will use the fermentation of a large fermenter to cultivate your E. coli. The problem is the cells. Okay, they want to lose this plasmid. Okay, and it's actually a big problem in the industry because, so suppose you are doing the fermentation with the, I mean with your recombinant organism, or with your recombinant bacteria who has the plasmid. So if this, I mean your organism lose the plasmid, it will go more faster. Why? Because if a bacteria have a plasmid, it has to use some energy to express that plasmid, right? I mean, when that plasmid will express, the protein will be produced. That means genetically modified organisms, they need more energy. But if somehow your genetically modified organism can lose the plasmid, so now it can use all the energy for their growth. So that's why they will grow faster, and then they can outgrow the modified one. Okay, that means they will modify it in the fermentation. So eventually, I mean your modified organism will be replaced by the, by those, I mean your modified organism will be outgrown, or at least replaced by the organisms who has lost their plasmid. Okay, so that means you will not get any product. Okay, that organisms will grow in the fermenter, but there will be no product. Okay, so that means we can say instability of plasmid in the modified organism. I mean we can term this problem as instability of plasmid in modified organism. Okay, so how we can solve this problem? One approach can be, like say you want to produce antibiotic, okay, by your organism. So what we can do, I mean say, as I just described it, you want your bacteria to produce antibiotic. So what we can do, we can clone the antibiotic producing gene into a plasmid, and then insert this plasmid into the bacteria, and the bacteria will grow. But as the bacteria would like to release this plasmid, what we can do, we can add antibiotic into the media. I mean in the fermenter media. So if we add antibiotic in the fermenter media, the bacteria now will not lose the plasmid. Even if they lose the plasmid, I mean that cell, that bacterial cell which will lose the antibiotic, it will die. So it cannot live there, I mean, because there is antibiotic in the media. So if they lose the antibiotic producing plasmid, they will die. So the problem of overgrowth or outgrowth will be resolved. Okay, by this way we can address the problem. But this approach itself has another problem. What problem? I mean, in this approach, you have to use antibiotic in the media, but antibiotic are not free, right? You have to buy this antibiotic, so it will increase your production cost. So then, how we can actually solve this? I mean, how we can overcome this? I mean, production cost issue. So one approach is we can modify the microorganism in a different way. In what way? Say, I mean, every organisms, every cells, it can be a mammalian cells, it can be a plant cell or bacterial cell. Every cells require some protein, which are essential protein for their growth. Okay, and there are gene in the chromosome of the cells which encode this essential protein. Okay, and this essential protein is a must need for the growth of that cell. So what we can do, we can delete an essential gene from the chromosome of the cell. Okay, and put this gene into the plasmid. Okay, so think this way. You want your bacterial cell to produce antibiotic. So to do that, you have cloned a antibiotic producing gene in the plasmid. In addition, you will do another thing. You will delete the essential gene from the chromosome of the uh, bacterial cell and insert that gene into that plasmid, and then you will insert this plasmid into your bacteria. So now what will happen? Your bacteria will always I mean, your bacteria actually will never lose the plasmid, because if it lose the plasmid, it cannot grow. Okay, so by this, so that, I mean, it will always, I mean, the plasmid will be always there. Okay, so by this way we can resolve the problem of instability of plasmid. Okay, a very nice, effective approach. Okay. Another problem of using recombinant bacteria is that it is difficult to recombinant bacteria to produce large amount of foreign protein and at the same time to grow to high cell density. Okay, I mean, if we want to produce large amount of products, what we need to do? The microorganism or the bacteria itself need to grow in large amount, because if there are lots of cells, then lots of products will be produced, but achieving these two goals at the same time is difficult. Why? Because the cell, have to partition its resources between production of foreign protein and cell growth. Okay, so I mean, a wild type cell, it can use all its resources for their growth, but this recombinant bacteria, they cannot use all its resources for their growth, because at the same time they have to produce the foreign protein. Okay, so that's why their growth slow down. So how we can solve this problem? We can solve this problem by this approach. First, grow cells to a high density. I mean, first produce lots of cells, then change the environment in a way that the resources will be shifted from growth to foreign protein production uh, environment. Okay, I mean, like, so what you have to do? So first we have to grow. I mean, first the condition should be like that. The cell growth will be higher. Okay. So by using that favorable condition, we will produce lots of cells. Then we'll change the condition. Okay. In what condition? To that condition where the cells can produce the product. Okay, so we can do this. I mean, we can achieve this approach, or we can perform this approach by using quiescent bacterial cell. Okay, so let's try to understand this approach. And to understand this approach, I will use a quiescent E. coli cell as example. Okay, so I'll try to explain how we can actually do that. Say, for example, you want to uh, produce a protein. Say a antibody. Okay, this antibody SCFB. I mean, the antibody is encoded by this gene, and you want to produce this SCFB protein by using E. coli cell, by using quiescent E. coli cells. So what you have to do? You have to clone this gene, okay, under PL promoter into a plasmid. Okay, so take a plasmid and clone your SCFB gene under PL promoter. Okay, you have to prepare or make another plasmid, and that plasmid will contain another gene, RCD gene, under PL promoter. Okay, so what's the function of RCD? I'll tell you later. I mean, we know the function of SCMB. I mean, this is our target product. So we cloned it into a plasmid under PL promoter, and also we prepared this plasmid, the RCD gene under PR promoter, and then we inserted this both these plasmids into our quiescent E. coli cells. Okay, the quiescent E. coli cells, they have a characteristics. They can grow at 30 degrees Celsius, but at 40 degrees Celsius, they cannot grow. Okay, so if you keep the quiescent E. coli cells at 30 degrees Celsius, they will grow very comfortably. But if you raise the temperature up to 40 degrees Celsius, their growth will be ceased. Why? Okay, let's talk about the chromosome of the, I mean, if we understand the chromosome of the quiescent E. coli cells, we'll understand why this happens. So the quiescent E. coli cells, they have a gene in the chromosome. It's called HMS gene, and this gene is important. Okay, so these genes can, I mean, this gene is essential to essential for the production of several essential proteins. Okay, okay. But in your quiescent E. coli cells, this gene will be a little different than the wild type genes. But yet, although they are different, they can encode. They can induce the production of the essential proteins. Okay. The chromosome of quiescent E. coli cells, they have another gene which is called CI857 gene. Okay, under PTRP promoter. Okay, so when at 30 degrees Celsius, okay, these genes, both of these genes are expressed. So as the HMS gene is expressed, it induces the production of essential proteins which are required for the growth of the quiescent E. coli cells. Okay, and this gene at 30 degrees Celsius, this gene, the CI857, it produces a repressor protein. Okay, and this repressor protein bind with the promoter of both this plasmid and this plasmid. Okay, and as these are this is a repressor protein. When this repressor protein bind in the promoter region of this plasmid cannot express. That means this gene product are not produced. Okay, so that's why at the 30 degrees Celsius, the E. coli cell, this E. coli cell, it will grow very rapidly, but it will not produce any product. It will not produce your target product. Okay, so keep keep the fermentation at 30 degrees Celsius for say a defined time. Okay, so once lots of E. coli cells are there, now change the temperature to 42 degrees Celsius. So if you change the temperature to 42 degrees Celsius, what will happen? What happens? What happens at 42 degrees Celsius? This repressor protein, which is encoded by this gene, get inactivated. That means there will be no repressor protein at 40 degrees Celsius. So as there will be no repressor protein, that's why these two genes, which are in the plasmids, can now express. That means this gene product will be produced. If the SCFV gene is expressed, your target product will be produced, and also this gene will be expressed. That the RCD protein will produce. So what the RCD protein do? This RCD protein can bind with this HMS gene. Actually, in case of the quiescent E. coli cell, this is a modified HMS gene. Okay, genetically modified HMS gene. It is modified in a way that the RCD gene product can bind with it. Okay, so at 40 degrees Celsius, the RCD gene will be expressed. That protein will be produced. So that protein can interact with the HMS gene and repress it. So as the HMS gene is repressed, so that the proteins which are essential for the growth of the E. coli cannot be produced. So that means the growth of the E. coli cell will stop. Okay, so only the all those, and as the growth of the E. coli cell will stop, so now those E. coli cells, they can use all their energy to produce this protein. Okay, actually that was the approach which is written here. Okay, so first grow cells to a high density and then to shift resources from growth to foreign protein production. Okay, so we can do it by using quiescent E. coli cells, and it was an example of that approach. Okay, so that's all for this part of the lecture. In the next video lecture, we'll learn about some more challenges and the way by which we can solve those challenges. Okay, till then, be safe. Thank you.